Hi everybody. My name is Simon, and I work at EfficiOS with Frances and a bunch of other great people. So I've been working at EfficiOS since February this year, and since then I've been working on the Babeltrace 2 project, which I guess if you've been here in the past 3 years, you've already heard about. It's been a long-running project. Today I'm going to give you a little update, but most importantly, since we're finally getting close to something that can ship, we felt it's a good time to start inviting people to start writing plugins and start writing their own component classes, as we'll see, to add support to Babeltrace for either new trace formats or new outputs, new analysis, things like that. So today, that's what I'm going to show you. So this is what the presentation is going to look like. So first, give an update about the project. Then just a few important concepts about how the Babeltrace library works that's needed to efficiently write the components. Then I'll give small examples. We won't go into very deep details, but it should be enough that you could get started writing something that reads your own trace file. In 4, I'll talk about if you want to make this more of a product and make it more production ready, what you can do. And we'll have a few demos along the way, hopefully it's gonna go well. So, a little status about Babeltrace. So first, if you haven't heard about Babeltrace, it has been started by Mathieu Desnoyers as part of the LTTNG project. And the goal being, as the name implies, to process and convert and analyze traces in various languages, or various trace formats. It's been used, therefore, as the kind of de facto reader for LTTNG traces for many years. But the goal of having support for many different trace formats has not really been a reality, mainly because of some shortcomings. For example, the intermediate representation used when you read the trace into something in memory was very tied to CTF, which is the format that LTTNG produces, common trace format. So if you were trying to read some other format that did not use the same concepts, it would be a bit awkward and not very practical. So in Babeltrace 2, we really focused to make this decoupled so that CTF uses that, but if you have your own simpler format, you don't need to deal with all these concepts that you don't really care about. So it's much simpler. In Babeltrace 1, there was also no external plugin system, meaning that once Babeltrace is compiled, you could not really add support for a new format and just point your Babeltrace binary to load this plugin and read my trace. Babeltrace would have to know about it when it would get compiled, so it was a bit harder to extend. And finally, Babeltrace 2 is the goal is that it's cross-platform on the 3 standard platforms. So as I said, we've been working on it for quite a long time, but the status today is that all the expected changes to the API are done. So maybe a year ago or more, Babeltrace itself was feature complete, but the performance was not up to par with Babeltrace 1, so that was not really acceptable. So in the past year, there were many performance improvements that were done. You can check Philippe Cou's presentation from Tracing Summit last year about that. That's really interesting. So doing these performance improvements required doing some API changes, so it had to be done before the initial release. And today we don't expect to do anymore, so it's pretty much stable. There's currently no documentation, but Philippe is working on that as we speak. So for the Babeltrace release, there should be some good documentation if you want people to use it. And RC1 is expected in a few weeks. Now, there's been a little impediment in that Philippe has forked a little, or his girlfriend has forked a little baby, so it'll be unavailable for a few weeks, but after that, we'll get it done. So yeah, a few important concepts that we need to start writing Babeltrace plugins. So in Babeltrace 2, everything revolves around a graph. So a graph is a network of interconnected components, some of them that produce data, some of them transform another, so produce, transform, and output data outside of Babeltrace. So you might have seen the same pattern in other software like Pulse Audio or FFmpeg, things like that. So you have sources that take care of giving data from the outside. So it can be a trace file, receiving from the network, or anything you can imagine. They bring the data into the graph. They send it to downstream components, which can be filters. So they receive data from an upstream component, apply a transformation, analysis, whatever, and send it downstream. And finally, you have source, you spelled my yeah, sinks, so in red it should be sinks, whose job is to take the data from the graph once it's transformed in what you want, and produce what you want. So if it's a visual analysis, it can pop up a window. If it's just convert between two trace files, it can be output in another trace file in another format, sent from the network. It can be really anything. And yeah, and the way that you configure these components, we'll see later, but the Babeltrace command line interface gives you some kind of standard layout like this, where you have many sources. They all get merged in a multiplexer, so that you can analyze them in a chronological order, sort the events, and then output them. But in reality, you can arrange these components in any kind of graph as long as they understand each other. The communication between them is done using messages. So a message is just the unit of information between one component and another. There are a few message types, the most important being these. So when you have when a component wants to indicate that I'm reading the start of a stream of events, so it sends that kind of message. Then the most obvious one is an event message. So every time there's an event that's usually associated with a timestamp, it sends a message downstream. So if you have a trace with 100 events, it will send 100 of these messages. And finally, once it's done, it says, I've reached the end of my trace file. Physically, it sends the stream end message. There's actually a few more, but just with these three, you can start writing something useful. And just to be accurate, when you think about how components are written later, I said that components send the messages downstream, but how it works internally, it's actually the opposite way. It all starts with the sinks that once they need to consume messages, they will ask their upstream component, please, if you have some messages, give them to me. And this will recurse. So for example, the red component will ask a filter, do you have some messages? And then the yellow component will ask its upstream components, do you have some messages? And eventually it reaches the sources, and those read from the trace files and then reply, yes, here are my events. So this is how it works internally. So the life cycle of a graph, how it works is that when you start creating a graph, when you create a graph, it starts as empty. And as a user, let's say you use the Babeltrace library, you can add your components and connect them as we saw on the picture. Once you've added all of them and connected all of them, you say, okay, I want to start. The graph gives an opportunity to all of the sinks, so the red thing, to create iterators on its upstream components. So that's what will let the sink query ask for messages from its upstream component. So all the sinks create their iterators. Once that's done, the graph repeatedly asks for all the sinks, go ahead and consume from your iterator. So, and this is in a loop as long as we're not done. So this is what makes the conversion process or the analysis progress, the things will pull events from, or messages, I should say, from the upstream, and it will make all the thing progress. And when, let's say, a source is done, it will finish, it will send its stream end message, or it can actually have multiple streams, but it will close all of its streams. And when it has no more messages to send, it will reply with end, a bit like if you read a file, you read the end of EOF in the file. But now it will reply, I have nothing more to give to you. So that will tell all the actuators downstream, well, it's finished, it's finished, it's finished. And once all the things, all the upstream iterators are done, it means the graph has successfully executed, and we're done converting. Just a distinction between Babeltrace 2, the library, and Babeltrace 2, the command line tool. So at the core, there is lib Babeltrace 2, which is a lib library that lets you, using bindings in C and Python, create a graph, add components, and do everything by hand. So it's very flexible. You can integrate it in your own program and customize it. But if you want to have the command line experience that Babeltrace offered, Babeltrace 2 is a command line tool that's built using libBabeltrace. And as I said earlier, it helps you if you just pass Babeltrace space back to your trace. It will just build you a kind of default graph that works in typical situations, the one that we've seen earlier. But from the point of view of libBabeltrace 2, Babeltrace 2 is just a user of the library. It doesn't have access to anything special. So you could implement a command line like Babeltrace 2 using the lib yourself. And also, yeah, with Babeltrace 2, the command line, so I said if you just do Babeltrace 2, your trace, it will give you a typical graph that works, and in the end, it just prints the events one per line as you would expect. But you can also pass a ton of parameters to customize the graphs. Say I want to instantiate exactly this component, and connect this port of this component, these components together. So it can be easy to use and give you the default behavior, or it can be complex to use but give you very flexible behaviors. So each one of the boxes we've seen earlier on the little drawing are component instances. Each component instance comes from one component class, which defines its behavior. So a component class can be written in C or Python. It can be either written directly in your application. So let's say I have a main.c or main.py that uses libBabeltrace 2. I create my own graph. Then I can just write in the same file the implementation of my component class that reads my trace file, and then tell graph.add component of this component class that I just defined. So it's just one file, it's easy. But after that, if you want to distribute it, so either use it in different applications, or use it from the Babeltrace 2 command line interface, you can build it as a shared library for C, or its own Python source file for Python, and that's what we call a plugin. So it's something that libBabeltrace 2 will be able to load, look up the component classes in the plugin, and it will let you use them. Oh, and also, just to make it clear, there's no link between the language of the main application and the language of the plugins. So I can make a main application that's in C, uses libBabeltrace, and use a mix of component classes implemented in C and Python. So we can load the plugins from C and Python, and vice versa. If I write a main application in Python, I can load some plugins implemented in both languages. So now I think you have all the necessary knowledge to understand your first component class. So I'll do the examples in Python because it's just much more, less verbose than C, and it's probably easier to understand. But the same concepts apply pretty much one-to-one to this if we were to implement it as C. There. So the first thing is, what do I need to write just to get started? To make a Python plugin, Babeltrace will look for files in its plugin path that are named bt plugin underscore something.py. So the something can be anything. It's not the name of the plugin. It's just it looks for files named like that and it runs them. In the file, the boilerplate consists of that line. You need to register your plugin. That little name thing here, it's basically for Babeltrace to know which plugin is calling it. So it's mostly for internal management. Just write like this. And foo here in quotes, that's the name of your plugin. So when you're going to use it on the command line or look it up, that's the name you want to look for. So let's start with a sync because it's probably easier to understand as it doesn't produce anything versus a source that needs to produce some data. So the job of a sync is to receive messages and do some useful work with it. So in my first thing that sync that I write, the only thing it's going to do is receive messages and print them to the standard output, and that's it. That will be pretty much the simplest sync that does something else than nothing. So the three main steps in the life of a sync is that in it will need to create some input ports. So in order to add the component and connect it, it needs to have at least one input port. And that input port will be connected to an upstream component's output port. In a callback called graph is configured, so this callback is called, init is called basically when you add the component to the graph. So if it's the first component type to the graph, I add it, init gets called. But the upstream components might not exist yet. So that's why we cannot really connect anything there. In graph is configured, that is called once all the connections, the user has connected all the ports together and is ready to start executing. So that's the opportunity your sync has to create some iterators on the upstream component. So that's where you would do it. And one thing that we need, maybe that's not totally clear, but we need to understand is that a sync component, typically it will iterate only once on its upstream component, but for some reason it needs to iterate twice. It could create two different iterators. And these two iterators are completely independent. If I advance one, the second one should not be affected. So if there's any state associated to iteration, it should be in the iterator and not in the component itself. But yeah, we'll see about that when we look at the source. So we created an iterator in graph is configured. And finally in consume, that's the function, the callback that will get called repeatedly by the library to tell you, well, consume from your upstream component, receive some messages, and do something useful with it. So I'll try to show you a simple one. I didn't think that I would not see the tree, but not like this. So here, my example. As I said earlier, I have a file name bt plugin underscore something.py, so Babeltrace will be able to load it. And that's about as short as it can get for a sync. So we have our boilerplate here, and here we have a class that defines our component class. You just need this annotation to tell Babeltrace that consider its class as a component class. Inherit from this base class that tells it's a same component implemented by the user. The init, so if we look at the parameters, params, it's going to be a set of parameters that can be passed either from the application, it can be from the command line, and it looks essentially like the same types as would have in JSON. So we have strings, numbers, lists, and dictionaries. So we can modify the behavior of your component like that, or like pass a path to the trace file, things like that. And Hub is if you implement your main application in Python, then you have the opportunity to, when you add the component, to also pass an arbitrary Python object that will be then passed to your component in its function. So let's say you read from a database connection and you have 10 components that need this connection, then you could pass it to all the same connection to all your Python objects and use it here. And obviously, if you use your component from the command line, then we don't have the opportunity to pass anything here. So first step, we create the input port as simple as in get, give it some name, but in our case, it won't really matter. Then, once all the graph is set up and we're getting ready to run, we create an iterator here, just called create message iterator on your port. And finally, in consume, so this gets called many times as long as there are things to consume. So we call next, which is the standard Python function to advance an iterator and get the next value. We get a message and then we'll print it. So if I try to run it, looks like this. So from the command line, it looks like we're calling Babeltrace 2, adding the current directory to the plugin path, because we wanted to find our plugin. And then using, is it the right thing? Using using the -c or minus component notation, I can add the component of this class, and just this part as a component. And finally, just because I want to have some data to have my sync consume something, I pass the path to a very small LTTNG trace, which will produce some messages. So if I run it, we can see that it prints one message per line. And if we look to see if it makes sense, then it was on an 8-core machine, or 4-core machine. So we get 4 different streams in parallel. The CTF trace supports packets, so we have the packet beginning message that we have not seen yet. If your sync doesn't care about it, you can just ignore it. Then we have a few event messages, and then at the end we should close the packet and close the streams. So packet and we have a few empty packets at the end. But essentially we close the packets and close the streams. So I think with just that you can start writing an analysis or a sync of all the data you need. And basically if you look at the API of the event message, that's where the real meat is. You can read the fields, the timestamps, and everything like that. It's another. Okay. Then the source. It's a bit more work, but not that much. In the init function, we need to also add an output port, like we added an input port in our source, in our sync, sorry. But we also need to create a trace class, stream class, and event class. So basically, we're going to want to send some events in our event messages. For that, we need to define what are the types of the event that we can send. And events are part of a stream, so we need to define what kind of streams we can have. And finally, streams are part of a trace, so we need to define what kind of trace we can have. It does need to be very complicated, as you'll see. After that, we need to define the source iterator class. So as I said, every time that a downstream component will create an iterator on your source, it will instantiate a new object of that iterator class. And any data associated with iterating should be in there, so that if you have 2 iterators and you advance one, the other one is not affected. Finally, in the iterator's next callback, then you need to return some useful messages. So as we saw, the CTF source produced the messages. You have to do just like that. So if we look at example source, that's pretty much the simplest source we can get. So the source is at the bottom here. The same annotation as before. It inherits from user source component. And then here we define for this source component class, here's the type of the iterator I want to use. So this is the class that will get instantiated when we create an iterator. So here, create a trace class, a clock class as well if we want to have timestamps in our trace, which is usually the case. Create the stream class, create the event class. Here, I give it this name. I have not added any fields, but in some more complex example, it will show how to add some fields. Finally, add an output port to send a message on. In the iterator, so whenever somebody creates an iterator on my source, I want to basically fetch on which port it is, on the stream class and trace class that I've created earlier, and then I'll instantiate one instance of each, so I have one trace and one stream. If my trace had 5 streams, I could create 5 streams using that class. And finally, now since I have only 3 messages, I just create them all right away, and I send them in the next callback. So here I have 1 stream beginning message, 1 event, and 1 stream end. So that's the most simple you can get. And then in the next callback here, that gets called every time that somebody downstream fetches messages from you. Here I just send them as long as there are messages remaining. So if we try to run it, I don't see very well. Tell me when you see source. So if I try to run it, here I see that my source produced 1 event as expected. And then, just for fun, let's say we want to put the 2 together. No. I'll just use run. I expected to be able to see on my screen. But basically, so here I have I've created a file that contains both of my source and my sink. I could have put them in separate plugins and loaded the 2 as well. But just think like this. So in my run command line, I just use the -c switch twice to instantiate 1 of each, so they will talk to each other. And if I run it, I see that my sink prints the 3 messages that I have indeed sent in my source. So I think it's quite straightforward. Okay. So these were really the big steps of writing either a source or a sink. I think with just that you can, start prototyping and start feeding your events into Babeltrace, or start taking what Babeltrace produces and do some analysis with it. But let's say you wanted to go a step further and make this more usable in real life. These are some suggestions. First, as we saw, there's a parameter when your component gets instantiated. So you can use it to pass usually some paths to trace files. It can be, if you want to enable or not some features in your component. The second thing would be to support the Babeltrace that's supported full query. So I don't really have time to talk about query in details, but it's essentially a way to ask a component class about details from a trace before you even instantiate the component. So it's like, do you support this? Like, I have a file here, do you recognize it? In the case of this query. So supporting this allows the Babeltrace CLI to automatically discover which source is the right one for which path that you pass. So if I take back this example here, I had my sink and I just passed the path. This is an example of the CTF plugin using auto discovery. So I pass a path to the directory, and Babeltrace asks all known source component classes, do you recognize this, And CTF sees that, oh yeah, there's a metadata file in there, and I can parse it. So it's most likely a CTF trace. So it says, yeah, I want to handle it. So if you support this, it makes the command line much more comfortable for your users. So instead of having to type params, lengthy params, you can just do Babeltrace to my trace. And finally, I think we have a pretty neat error reporting system. So this game, that's my main contribution in Babeltrace 2, because I complained to Philip that I thought that the errors were really not clear, so we wrote this. So really proud of this. So let's say I have an error here. You won't know about this. And I try to run like this, I guess. It will be pretty detailed. So starting with the root cause is at the bottom. So it will tell me that in my, I don't know where my pointer is, but it will tell me that in this component class and this iterator exactly at this time, in case of Python, I have the Python stack trace, but also every time it returns to a caller that, okay, well, since I called this and I failed and I also failed, and then it unwinds, it's like a big stack of error causes. And I found that this was really useful when you have an error. Previously, you had to search in the thousands of lines of logs, detail logs, but with this, it's just, you have the error right there in your face. So, in the case of Python, all you do is raise an exception. When there's an exception, it gets converted to an error code like this. But if you write your plugin in C, you have to yourself do it. So if you have an error code, you have to call a function to say, okay, well, append this reason, like I failed, but because of this. So if you use this, it makes your plugin a bit nicer to use for your user. So if you want more examples, you can take a look at the Babeltrace tree. The Babeltrace tree there's the main library that implements the core, but all for example, the CTF support or the whatever prints, I guess now I have a bug, but whatever prints the events one per line, that's called the pretty sync. They're all implemented as plugins. So if you want to look at how Babeltrace does it internally, you can take a look and do the same in your plugin. We've also started writing some plugins on the side just to test some things, and with the help also of Gabriel, my colleague. And there's a particularly interesting one. So Gabriel is part of the team at Polytechnique Montreal who build an electric race car. And they have some data that is output, so they sniff the CAN bus and record everything that passes on there. And it gives a huge, basically, trace file with timestamps. And right now, they're kind of writing homemade scripts every time they want to do an analysis. So in one afternoon, he wrote a basic Python source to read that and send it in Babeltrace. So we won't have time to look at the code, but I think it's pretty interesting. So he did and it gives a good comparison between Python and C. He wrote a Python version of it that was not too long to write and works very well. But I think reading this trace that has about 200,000 events, it takes about 20 seconds, so it's not super nice. So I rewrote it using the C API. It was a bit harder, but I think the performance improvement is well worth it. It's like under 1 second. So that shows that Python is really good for prototyping your components and trying new things, but once it works, and you just want more performance, then you can rewrite this. So that's pretty much it for me. I hope that you learned something, and we want to see you start asking questions on IRC and on this about Babeltrace too. So if you have any questions right now, I don't know what time. Yeah. Any time for one question
before the next speakers.
Great presentation. All this feedback. Great presentation. Is there any plans for integration with like Trace Compass and other things like that, as far as like parsing CTF files? in the future? Because I think, if I remember correctly, they have their own Java implementation of this.
Yeah, so actually wrote the first version of that many years ago. But yeah, it's a completely different system that's not really... so I'm not aware of any plans of integration. I know that Trace Compass is moving to, we'll see it in the next presentation, is moving to a client-server architecture with the backend just providing data. So if somebody wanted to write the backend of basically this Trace Compass server using Babeltrace instead, then why not? I'm not aware of any concrete plans to do it though.
Thanks.
Thank you.